hopefully some of you will be able to relate and not crash a machine, and not only not crash a machine, be able to do some very interesting projects. So it's a process to figure this stuff out, and this is not easy stuff. But now that you've got a little bit under your belt as far as the stepper, do you have any questions for me? Because I certainly am not an expert on it, but uh, if you can make a motor turn from direct control in a PLC, that's your first big goal, is to get the motor to actually turn, and that's why that downloadable program is given to you so that you can get it to just turn. And those directional arrows where you were told, do this, do this, do this, do this, do this, that was for a reason, because that's for a reason, because we want you to try it to see if you can get it to actually motor before you start writing a lot of programs. Uh, one of the things that I did wrong when I crashed that machine was I'd written a bunch of programs and then tried to fit the actual motion control to the programs, instead of getting the motion control programs working first and then trying to get the programs to work around it. So I built a Taj Mahal that didn't have a foundation. So your foundation in these programs is the programs to get the motor to work, to basically get it to turn. And from that point on, then you start adding your extra stuff. And you can have some of that written or thought out, but don't spend too much time on those parts until you've got it to turn. And at that point in time, then you've got control of it. Okay. So these instructions, these enable and all this kind of stuff, are instructions that show up again and again and again, and they show up in AC and DC motors and all that kind of stuff. But the enable one and the reset are very, very important, that you have those, so that if something does go wrong, you can always disable it and then start over again. But you basically have three commands. You have a motor run, or motor just velocity, and then you have a um, move absolute and a move relative. Okay, those are your three basic commands. And then you can also stop. If you have a motor velocity, you have to have a stop button. You have to have a stop that'll stop it at some point in time. You can use this for things like jog. You can use it for if you're continuously running, you can do it for that. But the move relative and the move absolute are your two best friends. Okay. Now, kind of picture yourself, where will you do a move relative and move absolute? Well, with this today, the one that you're given, you do a move absolute, because you're told to move 3 turns one way, then 3 turns another. You can jog it, but at any rate, then you had a homing button that'll take you back to 0. So if you have that capability, you're pinned to the move absolute. You could go 1,000 revolutions in the forward direction, and if you hit that home button, that home one, it will unwrap you 1,000 turns going the other direction. It'll go back to where it was when it hit home originally. So you can go way, 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 way out, and it will bring you all the way back. And it'll find exactly where it was when you hit home. So some applications use that. Other applications could care less. So let's talk about a couple of these applications for just a minute or two, okay? Okay. Move relative, all right? If you're never going back to a home position, you can do move relatives all day long. And they would be for something like where you've got like like a conveyor that you're putting parts onto. Okay, so this is a vertical conveyor, and when you get to a certain position, then you're going to take them off or whatever. But this thing is constantly rotating. Let's say it's rotating in that direction, okay? So you stick them on here, and when they get up to here, they turn off, okay? So what do? You advance to a position, then then you stop, and then you put the part on, and then you turn it again. So you're constantly turning in the same direction, a certain amount, starting and stopping, starting and stopping, starting and stopping, starting and stopping. Now, why would you use a servo or a stepper for this? Because you need to know exactly where you stop. You need to know exactly then you need to hold torque at zero speed. Okay? An AC motor will not hold torque at zero speed. A DC motor will not hold torque at zero speed. A servo will, and a stepper will. A stepper doesn't have as much torque, but if you don't have much torque need, then it will hold. It'll do it. Okay. Now I want to talk a little bit about economics of these things. Okay, economics. All right. So in the realm of PLCs, which basically is on-off control and analog and all that kind of stuff, you have a couple of big guys, a couple of big vendors, and then everybody else is kind of relegated to nothing land. So you have Allen Bradley, you have Siemens, and then you have maybe a few Japanese in here. And then you have a few others, but not many. In the motion control industry, it is exactly the opposite. In motion control, you have hundreds of small vendors that have a niche. And they might do specific applications for something, but they've developed a way of doing it that is the most economical, and you can't beat them. Okay, so it's splintered, this area. Now, you do have some bigger controls like Fanuc, and they do have um, a CNC controller, and there are a few others that do have that as well. But in general, you're it's either you do it yourself or you find a vendor who specializes in that type of application. But there's not a lot of people that actually sell this equipment other than, well, a lot of people use a PC or Raspberry Pi and they program it and then they sell it. Okay, that's how this is done in motion control, a lot of it. I had an application a few years ago now, it's been quite a few years ago now, but it was for a router to cut out where a screen was to go in a screen door. So they wanted to actually router out around the edge of that opening and make a nice opening for that. And they used a two-axis stepper motor two stepper motors that actually controlled the router going around the axis, around the edge. And they bought the whole thing, computer, everything, for $3,000. I looked at that and said, you cannot possibly do that for less money than that. They basically had that market cornered. So for something that would go around and do a two-axis, like follow up, it had rounded corners and would take a router and move it around, $3,000 was an ungodly low price for that. You couldn't beat it. Anyway, so you basically in this market, you look for somebody that's done it. You look for somebody that's done whatever it is. But then if you come up to this wall that says this has never been done before, and you have one of two choices at that point in time. You can either go out and put out a specification and ask the world who wants to do this, or you can do it yourself. And the tendency always in the past has been to find somebody that could do it for you, and then they would come in and sell you that as a turnkey solution. But in today's economy, it may be better for you to do it yourself. And then you also have to ask the question, could it be done better with a robot? In today's economy, you have to say, well, a 30, 40, $50,000 robot do the same thing. And you have to consider the fact that even though the robot may cost you more initially, the engineering cost of putting together a, a discrete system might cost you more in the long run. So you have to weigh that as well. So you've got robots on one side, you've got vendors on another that are beating your door down. They've got the answer to your solution, to your problem. And then you have the actual problem, and you have to decide whether or not you're, how you're going to go to war. So basically that's, now on the PLC side, this has got more interesting as time has gone on, because what they used to not be able to do, they now can do. And here are, in that little program controller that you have, okay, they have a Gen 2, okay? Now, Gen 2 has just been released by Siemens. This is one of the areas that they went after. I want to show you this. These were things that they couldn't use, they would not do until in the 1200. Now they would do it in the 1500, but they would not do it in the 1200. They had these all grayed out, but now they don't. Okay. So what they have here are what they call CAM operations, and a CAM operation is nothing more than, if you've seen a CAM, what it actually does is it allows you to have to like go around a corner and have a smooth operation. The bad side of a cam is that it wears out. It's a mechanical device that actually, as it rubs, over time, if you do it enough times, it'll actually change positions, okay? But an electronic cam doesn't do that. Electronic cams, you program, and they do the same thing every time, okay? So if you want to draw a circle with two motors, you would get a CAM program to maybe do that. Yes, sir.
So a CAM program is different than computer-aided manufacturing, or is that the same thing?
No, it's different.
Okay.
So these basically are instructions that are inside the PLC that basically allow you to have two motors that are coordinated, or three motors are coordinated, or four motors are coordinated. All right. Usually it's just two. So you're working one in the X direction, in the Y direction, you're turning so that you make an outline of what you want. In other words, you don't have to go to a corner and then you go to another one, do another one. It's basically they're turning based on an arc that you want to create, and it'll repeat it. It's a repeatable, controlled arc. It's not a this time it goes this way, next time it goes that way, because I had a little bit different torque in the system, because I had different loads. It's not dependent on load. Every time it's repeatable. So what we're talking about here are those kind of instructions, and here they are. Here's some of them. Here's what they are. Okay. Synchronous motion. Now, how do you, I've not used these, by the way. I'm not an expert on this, but how do you start breaking this down? You start looking at these instructions and saying, I understand what a cam is. So here's starts gearing, start camming, gear out, cam out. This is the turning it off. Okay. So basically the other axes follow a lead axis. That's what it boils down to. All right. So these would be applications. So if you really want to know that, you could actually use this little PLC, which is this size. It's the same size as the one you got, Siemens. Looks a little different. I've not seen one yet, but it's evidently it's sort of basically the same thing that actually can do all these applications, right? So let's burrow in and talk about some applications. I would much rather talk about an application than I would about instructions that I really am not that familiar with, but I'm going to talk to you from the application side. Okay, so these are some applications that you could perhaps maybe put together. Now, if you wanted to work for Libion's Ford Company, which I would not necessarily recommend, but on the other hand, you might end up working for these guys. So they bring in company X that sells a dynamic cross scoring system. I don't want to save that. No, Ted. I want to get rid of it. So here is your continuous glass coming down the line. And at some point in time, they break it, and then it becomes pieces of glass. Okay? That's what they do at Libion's Ford. They break it. Before they break it, they have to cross score it. In order to do that, they have a machine that's sitting up here that goes at an angle. Okay? And you have more than one. And so what they do is, as the line is going this way, they're going across, so that when they're matching the speed to an extent, to a fraction, so that this drive is matching to that speed at a certain angle. So basically, when they're cutting the glass, these pieces of glass, they're actually cross scoring, and it looks like that. That's exactly what it looks like. And you can actually see the score lines as they go across. There's little oil drips, they drip oil as they go as well. So, all that being said, could you do this with these motion control applications? The answer is yes. Absolutely. Here's another one. You're making a fiberglass tank or a fiberglass pipe. Let's say you're making a fiberglass pipe. So what you're wanting to do is, if you look at this cross-sectionally, I'm just looking at like this, taking that and looking like this. You want to send the fibers down at an angle. And that angle has properties that are best for that particular application. Now, I don't know what that angle is, but you'd say, okay, now I'm turning this, I've got a shaft here and I'm turning this rotationally. I don't know what this angle is, but I have to start out and I want to be able to make a certain angle, which is exactly the same thing as this is. It's exactly the same thing. But on top of that, I want to take my ribbon, which is about yay thick, and it's styrene soaked, thousands of fibers that are basically just a bunch of fibers, but they've got glue in them. And it basically forms like a tape. You would call it a tape, although it's not really a tape. It's just a bunch of fiberglass fibers, okay? So you're taking all these fibers and making a tape. And what you want to do is, if you zero in on this thing right here, what you want to do as you're starting each row, here's one row, here's your tape, okay, here's your tape. So when you start your next row, you want to overlay it just a little bit so you don't have any holes, but you want to lay it right next to that one. And then you want to lay the next one right next to that one. So there's no gaps. Okay, no gaps, but just barely overlay it. So if you look at it really closely, you'll see one tape and then the next tape. Yeah, I'll do it better here. Here's one tape, and here's the next tape, and here's the next tape, and here's the next tape, et cetera, et cetera, et cetera. That's how they do it. That's how they make fiberglass tanks. So you're responsible for making this tank making machine. How do you do that? Right there's instructions. And you can do them all with those cam instructions right there. Okay? How do you do a grinder? We say, get your grinder out and you start grinding, right? No, that's the machine I crashed. I don't want to belabor that, but that's what you have to do in a grinder is you fast forward down, and then you very slowly move that little bit. And then the grinding wheel is a circular wheel that has depth to it. So after you've measured the ground part, the part that you've done the grinding to, so basically this wheel is spinning at a high rate of speed. This is called the spindle. But it's rotating at a high rate of speed. So you have a spindle drive that you're not coordinated to. And then you have this thing that's grinding, and it comes down here, and this wheel comes down on your part. And you want to make a flat surface, and you only want to take off a little bit. But now, as you are measuring these parts, what you do is you say, okay, now the next part is a little fatter than the last part. Why is it a little fatter? Because my grinding wheel actually took a little bit of grinding off. It took a little bit of my grit. Okay, just a little bit, not a lot, but a little bit of my grit went away. So what you want to do is, as this goes a little shallower, not a lot, but a little bit, you want to make this go a little deeper. Just a little bit. Okay? 1/1000th of an inch or 2/1000ths of an inch. Just a little bit. And that's how you do it. Not a big deal, but that's how that's done. Okay? Single axis. Is this a coordinated motion? No, not a coordinated motion at all. Now, there is some argument that you do not want to use a servo for this application, but rather use a stepper. Why would you use a stepper as opposed to a servo? Well, the stepper motor does not have a PID algorithm in it that if it doesn't quite make, in other words, here's my part, and here's the grinder. Right, it's spinning. This guy's spinning. This guy's spinning. This part, if there's a little bit of a rub here, this guy can't make it all the way. Let's say he's supposed to go 3/1000ths and he can only make it 1/1000th of an inch. Those other 2/1000 of an inch, he says, I gotta go, I gotta go, I gotta go, I gotta go. And he will push harder because there's a PID algorithm, push harder and push harder. And that could cause this grinding wheel to actually explode. So a PID algorithm has to be tuned in such a way that it does not keep pushing, 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 because if it does, it could make this thing rupture. That does happen, but then you can say with a stepper motor, it tried, but there's no feedback. So basically it tried, pushed, didn't push any harder, didn't push any harder, and then it retracts. You see the difference? There's no additive there's no integral of the error with a stepper motor, where if you use open loop as opposed to a servo motor, which does have closed loop. Okay. So those are some applications of these two devices and how you would set them up and all that kind of stuff. Anybody have any questions about any of this stuff? Like, you're very quiet. Does anybody have? Are you ready to go out and do a single axis motion control now? You could, by the way. Doing these two applications, you're armed with enough knowledge that you could probably ask the intelligent question, be able to go through and set up a single axis motion control or a multi-axis motion control as well, if you so chose. Now, the feedback is important as well, and the feedback has to be quick. So you have to be able to see enough feedback in 1 to 5 milliseconds to be able to make a judgment, because you need to run your PID algorithm every 1 or 2 milliseconds. Okay? On the tank over tank, there is a little motor, and if you have taken the EET 4450 class, it's lab 8. Okay? Lab 8 is controlling of that little motor for speed control. The encoder on that motor, if you turn it full speed, gives you, I think, 17 pulses per 10 milliseconds at full speed. Now, you ask maybe the question, can I run a PID algorithm with only a number that ranges from 0 to 17? The answer is not very well, because you go from 16 to 17, that's about 5% of your total movement. So do you want to be doing this all the time, going between 16 and 17, or 15 and 16, or whatever, and doing that jiggling back and forth? Or would you rather have a number that would maybe go between 0 and, let's say, 170? But in order to do that, you have to read it only every 100 milliseconds. And you can only make an adjustment every 100 milliseconds. So, what's wrong with this application? The encoder is cheap. You say, well, buy one with more pulses on it. Well, you pay more money for that. So you get these little cheap ones from China that basically only give you a few pulses per revolution or whatever. And you can say, well, that's okay. It is if you've got a little robot that you're trying to turn and you don't care. It's kind of cheesy and you don't really care. But if you're trying to make money and trying to make a process run, you all of a sudden say, I need to put something together that's more utilitarian. It gives you, maybe 100 pulses per millisecond at your speed, whatever your speed is. Follow me? You need to get something that your range of your number that you're actually going to do your PID algorithm over is giving you information and being able to give you that information in a timely manner. And usually the answer has to be done in 1 millisecond or 2 milliseconds. It's got to be quick. It cannot lag. So that's why you pay more money. That's why this has to be done kind of, you got to try it out. Most of these applications you got to try out ahead of time to see if they're actually going to work. And you want to try it out in a way that doesn't jeopardize your startup. So if you can try the system that you want to try out ahead of time, jury rig it up, make it all look, whatever, and see if it holds under those circumstances, then you can maybe move that forward and get that into your manufacturing operation. Otherwise, you're going to have some horrendous surprises, like that encoder that only goes 17 pulses in 10 milliseconds. That's not good. My only choice was to up the scan speed. Okay, I had to go to 100 milliseconds. I couldn't use 10 milliseconds, or I couldn't use 5 milliseconds, or whatever. I had to go at something high to give me a high enough number so that my numbers actually meant something. So if you're only one of 17 as opposed to one of 170, how would you like to do an averaging of one of 1/7 over that other? You don't want to. You really do want to be able to in 1 millisecond to be able to see 1,000 pulses or 100 pulses, at least 100 pulses. Okay. This is all part of the process of looking at an application and trying to figure it out and making some heads or tails of it. Okay. The other side of the coin is the torque. And I don't want to get too involved in torque, but torque is force at a distance, at an angle, and you better be able to understand how much torque you have that you need in order to make something accelerate or decelerate to get to the speed you want it to get to and how fast you want it to get there. I was asked back quite a few years ago now how to size some servo motors. I said, I don't really care. I said, I'm not trying to make a product. All I want to do is fit the bolt holes. So I bought the servo motor that was necessary to fit the bolt holes that I had previously from what was already there. I didn't really care because I didn't have to worry about speed. But you do. You have to be able to say, I want to be able to accelerate to a certain speed this motor in order to do whatever I want it to do. I want to move a box. I want to move making post substitutes. I want to move the box over so far, so fast in order to meet my speeds. So somebody's got to design all that out. Usually it's a mechanical engineer that designs that out and gives you the torque, and then you go and buy the motor, or he may buy the motor, and all you have to do is program it. If you have to program it and figure it all out, I guarantee you that there are going to be mistakes. First time out, there will be a bunch of them. So you're going to have these trial by error and all that kind of stuff. And I don't want you going in and saying, oh, I can do any kind of motion application you want me to do. Yes, you can, but it's going to take you a while. And it's a trap if you just say, I can do this in 3 weeks, or I can do this in 4 weeks, or whatever. Some of these applications are going to take you, I don't want to discourage you, but they're going to take you months instead of days or weeks to get them up and running. Okay? But they're worth it in the end if your company makes money at it, and that's why they pay you, is to make decisions like this. So you have these what should I do and how should I do it? Well, servo controls, stepper controls are valuable, and here's the instructions list that you can use kind of as a starting point. Say, now which one of these and how would I do this? And single axis motion control, easy. Multi-axis motion control gets a little bit more complicated. This is where we're at. We're using this for the Rubik's Cube. The single axis steppers is what we're turning the Rubik's Cube with. You say, you're using the same exact program that you're doing for the Rubik's Cube? Yep. Little stepper motors. What you're doing right now is the same as what we're doing with the Rubik's Cube. Okay? The same, exact same motor. Exact same, those motors that you're using are the ones that we're using for the Rubik's Cube project. Anyway, they're cheap. Motors are $10, controllers are $20, so for an axis you have $30. 6 axes, $180 and you're done. We're building those ourselves. So anyway, you're looking at the guy who's building them right back there. So that's, anyway. Any questions about any of this stuff? I want to go back and talk about a little bit more about, oh, and by the way, I don't have a huge test for you at the end, but we're going to have a take-home test, and it will include not so much this stuff, but maybe a little bit of it, but over the course of time, I'm getting myself kind of prepared to do some of this stuff. This is from that book that we kind of call our book. Now, this is not the original one with the one that for the farm. This is the second one. I've started developing this back when I saw the farm one wasn't going to work. But this is a combination of a lot of parts and pieces from various places, and I want you to understand some of this, not that you're going to have to be able to answer a question just from me, but that you can answer if you want this is for you to have. This is kind of just a general compilation of stuff that I found, and you can take this stuff, and some of it is very, 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 very good. Okay, now they talk about here about the motor, and we talked a little bit about sizing the motors and all that sort of thing. And I'm not really sure how far to go with this today, but I do want you to know that I'll pick some of these problems. They will be almost identical. Change the numbers. That's all I'm going to do is change the numbers. But you can find these numbers in here, these problems in here. And I want to ask a few of them. Not a lot, but a few of them. And just to kind of warn you that it's going to be kind of hunt and peck to find them, but not a not a big deal, but it's a deal. Okay, now I want to go down and talk to you about control. Something that's near and dear to me is these starter circuits, okay? So this is how a starter circuit is pictured in what we call a three-line diagram. Now you did a one-line diagram, but this is a three-line diagram, okay? And you can have, here's your fuses, or you can have a circuit breaker. So the symbol here is a fuse. That's what that is. Now, you can also have a breaker there, and that breaker symbol is somewhat similar to that, but it's just a little different. I'll show you what the breaker symbol looks like, kind of. There's two or three ways of showing it, but it would be all one, and it would be like like a like that kind of a thing right there. Okay, so this would be a dashed line to show you that they're all coupled together. Okay, and that would be a breaker symbol or something similar to that. And there may be something over here as well. This is either a breaker, a CB, or an MCP, motor circuit protector, one or the other. And this is one of the symbols. This is a circuit breaker, and there's an MCP, which is a little bit different, but it looks kind of like that. And the dashed lines signify that it's all one unit. Okay? Now, if this thing turns off, they all turn off. If the fuse turns off, just the one fuse turns off, and you could have single phasing, which is a bad thing. Okay? You want to buy a fuse package that has some kind of a way that says if you do use single phasing, that it will turn itself off. But that's not what this shows. This does not show that. But here's one way of doing it, here's another way of doing it, and then you drop down with two of these lines, and you come down like this does, and you come down through a transformer, 480 typically to 120, and then you do your motor starter circuit. Now the only difference between this and what I'm used to is we always fused the primary and one side of the secondary. Okay, so this would be the primary and then the secondary. And then you would fuse the one side of the secondary. And then you drop down and you would have your start and your stop, and you would ground this side. Okay? That's a simple start circuit, simple start stop circuit with your three overloads and the overload symbols right here, and then your contactor. So this is what you took apart the other day, this part right here. All right? You do not do this, you do not do this part. Okay. This is the disconnect, the breaker or the fuses, then the control circuit, the overloads, and then the motor. These are typically called T-leads, T1, T2, and T3. Okay, and the symbol down here is the motor overloads. These three overloads that are there. Yes, sir.
Are the overloads normally connected to another device, like a contactor of some sort?
No, the overload, there's two terminals. Okay, so your overloads come down to two screw terminals on the side, and you probably saw them on the side. You didn't know what they were, but there's two screw terminals on the side, and that is this right here. Now, they show you three, but there's usually they're just one. Most applications that I've seen have this, and then they have this, and it's called OL. Okay, one, and then you have your neutral. That screw terminal on the side is that contact right there. And that contact is off of these heaters. These are the heaters, physical heaters. And when these heat up, any one of these three get too hot, then it turns this off and it drops out this circuit. Okay. There's no physical touching between these 460-volt wires and that. They do not touch. They heat up these overloads, which then open that circuit. It's heat that breaks the circuit. There's no voltage. There's no current going. There's no current from this circuit going to this circuit. It doesn't happen.
What does it cut off? Like
This right here is okay. So you have a little the old style was a heater, and it actually heated a liquid up, and that liquid then would be like solder, and it would flow. And when it flowed, it would release a spring, and that spring then would open this circuit right here.
Right, but that OL circuit, where does it get, would that be connected to the motor? Would that be
Yeah.
Okay.
No, it's
Oh,
not
okay,
connected
so
physically to the
top
motor,
ones
it's
are
connected to the,
connected to the bottom one.
yeah, this,
Okay.
this is, these are the heaters.
Right.
They physically heat up a little dash pot. And that little dash pot then spins a little contactor that then opens this little guy right here. And that's that. Okay. You got it. Good. That's important. Okay, that does, now single phasing is talked about here. And single phasing is bad. Why is it bad? Because your motor will burn up. It gets hot too quick, and it will burn up your motor. So single phasing is why most people use circuit breakers or motor circuit protectors instead of fuses. Or if they use fuses, they have that little that little thing on them that says, okay, you did one, well, shut the whole thing down. But that's the problem with fuses. You have to protect yourself against single phasing. Also, they talk about large motors. Large motors. Oh boy, I do not like large motors, okay? There's no difference between large motors and small motors as far as I'm concerned until you get to really 2, 3, 400 horsepower motors, and all of a sudden, all these special rules pop up. You can't start them in more than once every, you know, oh my goodness. Then you start thinking about how do you protect yourself against that? You don't put that in a programmable controller. You have to put that separately, or else you might mess up and somebody might change it, and it might mess up your motors. If you get too big of a motor, what do? 400 horsepower, 500 horsepower, what do? You look for the power guys to say, do you want to go with a medium voltage starter? Medium voltage starters are in the thousands of volts instead of the 460 volts. So you go into the medium voltage starter business, and that's different. And that's the control circuit for a medium voltage starter is the exact same as for a regular starter like what we have here, but the insulation and the protection is totally different based on the fact that they have to protect against a larger voltage jump, and they have to do that, and that's what they pay power engineers for. That's not what they pay controls engineers for. I just do this and say go for it. So in most applications, you don't have to worry about 400, 500, 600 horsepower motors. Every once in a while, you might have to, but not very often. So you worry about 40s, 50s, 100s. 100s is about as big as you probably do in most controlled applications, okay? Maybe 200 now and then, but not often. But lots of 20s, 25s, 40s, 50s, that type of thing, all day long. Start, stop, whatever. But then when you get big, you have to ask the question, do you have a requirement that it not be started more often than, and then they tell you, and then you have to go back and you have to figure out how am I going to do this. Today I would do it with a fail-safe or a safety PLC. I would use a safety PLC and put a password on it and not let anybody else have at it, and then you've got it. But if you don't do that, you are always inclined to wonder if somebody's going to come in and make changes to it. Okay, so that gets you a little bit down that road. Yes, sir? Do you have any questions? No, you're all set?
Not really, yeah.
So that's where safety PLCs come in. So you start using safety PLCs for things where you know, you wring your hands and say, I can't do that. I have to have, I can't let anybody else in, so I have to do things with safety PLCs. And that gets you into the safety side of it. Okay. So here is a wound rotor, wired rotor. Anyway, never done one. Maybe I have, I just didn't know that I was doing it. But again, you start and then you add more, you take away the resistance as you get up in speed, and that's kind of how that's done. You have to look at these things because this does require some extra starting. And again, I'm not trying to tell you how to do these, but I would all of a sudden turn over to the safety PLCs if I was going to do it with the PLC. A motor can become a generator if you turn it off. When you turn it off and it's still spinning, it becomes a generator and it pumps electricity back into the circuit. And you have to be careful for that. You have to be aware of that. So what do you do? Apply some kind of braking. Ask the mechanical engineer, what do you want to do about that? Don't assume that they know very much, though. Usually, the mechanicals they buy the motors. All you got to do is bring the electricity up to it and be able to start and stop it. If they get really fancy and they have a brake in there, then they'll have to tell you that they put a brake in it. So when it's off, it breaks. And usually it's a mechanical brake that just grabs the shaft. And hopefully that's all you need, and it'll come to a real quick stop. But most of the time, you don't have to worry about that. But they're the people who have to pick that out and have to tell you that that's what they want. This is kind of thing that you've already done. I'm not going to go belabor it, but there's a bunch of these circuits that are down here, and boy, are they ever, they just get worse and worse and worse and worse and worse. But that's good, because now this is the kind of stuff that people stand around water coolers and argue about for days and weeks on end. So here is the circuit for 3 places where you can stop. Now, you all understand that this button and this button are at the same place. This button and this button are at the same place. This button and this button, right? This button and this button are at the same place. They're one start-stop station located in one spot. This button and this button are in one spot. This button and this button are in a spot. All right? That's what this circuit is. Okay? So you could have a start and stop switch for your motor down at the motor. You could have one at the such and such a place, and you could have a third or fourth place that would do the same thing. And every place you have, that you would have another set of these. So you can start from multiple places. You can stop from multiple places. Do you trust a lockout at the motor? Some people do. In other words, if you lock out the stop button, do you work on the motor from there? I wouldn't. Honestly, would not. Go to the disconnect, put a padlock on it, and then you can work on the motor, okay? Closest I ever got, and I'll end with this, was working on a project in Ashton, Rhode Island, and I went to start the lineup, and the guy came down from there was a oven, and he was on the 3rd floor of the oven. He came down and said, "Who started the oven up?" I said, "I did." And I didn't think about it. He said, "I was up there working on a motor on a shiv," and he said, "I had it working where I could, if it did take off, I could not be hurt." But he was actually working on a shiv on a motor. And he didn't lock it out. He didn't nothing it. I felt so bad. And yet, if I would have started it up and if he would have gotten hurt, it would have been his fault because he didn't do anything about it. He didn't lock it out or anything like that. So definitely always lock things out. Always for the courtesy of everyone. And this sounds ridiculous, but you need to yell. You assume that you can start it up, but you still need to say something like starting it up or starting the motor or starting the line up, and you yell it up so that everybody can hear you. And it sounds ridiculous, but the old expression, fire in the hole, is an expression from welders. But if you're welding above and the welding is going to come down on you, you say fire in the hole. And that expression kind of leaked over into most applications where everybody has to be heads up to know that something is happening. So I don't know if you yell fire in the hole. I don't know if you yell I'm starting to line up or whatever. But it's your right to start a lineup, push that button to start a lineup, because you're the engineer starting the stupid lineup. It's your responsibility to start it up. If there's no lockout, no tag out, and everybody says, well, you gotta have lockout, tag out. Yes, you do. And you also have all these other things going on. In the midst of a startup, things get strange and people get tired. And if you've been working for 7 days, let's say you've been working for 3 weeks, seven days a week, 14-hour days. Okay? Is that unreasonable? Nope, that's not unreasonable. That's why they pay you. And you get paid well. But at the end of that, I always, at the end of about 2 or 3 weeks, I had a feedback in my own mind, and this is what it was. I'd put a tool down, and if I forgot where I put it, I put a screwdriver down and set it down, and I forgot that I'd set it there. That was my key, that tip off that you got to get a good night's sleep tonight. You got to go, whatever's going on by 7:30, you got to go out and get yourself a bite to eat, and then go to bed. And that was my way of telling myself, you can't keep doing this. So again, I couldn't do it today if I had to. I'm 76 years old. I could not possibly do this today. But you do not have that problem. You're not 76 years old. But be aware of the fact that in startup situations that everybody's going 10 different directions, 100 mile an hour, and you cannot let that attitude take over with you. You've got to be safe, and you cannot do something stupid. You can do things stupid, but it's your responsibility to not do things stupid, okay? And somebody tries to make you do something stupid, it's your responsibility to say, nope, sorry, we're going to do this right. So that's your responsibility to correct them and say, nope, we're going to do this the right way. We'll start it up when everybody's ready, and I don't think everybody's ready yet, or whatever. So just be aware of the fact that you're responsible as well. And that's, people do get hurt, and you can't help 100%, but you can certainly minimize it by being not stupid. And whatever. I'm just telling you. Um, and you say, is that going to be the rest of my life? No. There's a nice thing called being a manager. At some point in time, you want to be the manager instead of the worker bee. So you want to work toward that, and then at that point in time, you tell other people what to do. And it's not that you just sit there and drink coffee, but you have some interplay and you do some of it, but you don't do it all. And let you know you'll move along if you do this well. If you do things well, you will get advancements. I will promise you that you will have opportunities. Okay, I can't promise you where, when, or how, but you will get your opportunities to advance. So we don't have enough people like yourselves, is what it boils down to. There's not enough people doing automation in the United States for us to be able to do what they want to do with bringing stuff back and doing all this kind of stuff. They've let it go too far. Now, I'm not getting political, I'm just telling you. They've let it go to the point where it's almost impossible to bring it back to what it was in the 1970s, 1980s, or to make it automated, a smart automation today, which would be, with AI and all that kind of stuff. There's not enough people, and they need people to do this kind of stuff. Shut it down.